Today we are continuing on electronic section 21.2 operational amplifier circuit. So far we have looked at comparator circuit. This is a comparator. Now we are going to look at two or more circuit: inverting operation amplifier, non-inverting operation amplifier. The difference between these two circuits is that there is a what you call negative feedback, a feedback to the inverting input. Same as here. Let's just review. This is the symbol of the operation amplifier circuit. We have a negative terminal called the inverting input, and a positive terminal called the non-inverting input. And that is the supply voltage, positive, negative. It allows us to have an output that is positive and negative. That means to amplify the positive portion and the negative portion. Right? So basically the inverting input, whatever you put in, it invert. Non-inverting, it just amplified as well. Whatever you put in comes out amplified. And the output is given by the difference between these inverting input, V plus minus V minus, and then you multiply by the gain. Because ultimately, the operation amplifier is to increase the amplitude. Right? So A0 is the gain of the amplifier. It's something that is determined by the engineer who designed the op-amp. We have no control over it. That is the input. V plus minus V minus. Okay. V plus minus V minus is the input, and there's the input impedance or resistance. That's the output impedance, output resistance. And then our open loop gain, A0. Okay. It's fixed by the engineer. And we take the output from the earth line. Right? This one is the earth line, the 0 volt line. That's output voltage, V out. And it's equals to that. So basically, it's the difference between the input, and then you just amplify it. Then characteristic of the operation amplifier. We want an infinite input impedance, so that whatever we put in, all the waveform, all the signal goes to the input. That's the purpose of infinite input impedance. So we don't have to worry about the source impedance. Then we want the output impedance 0. So that, I remember, this is an equivalent circuit. It's not the actual circuit. It just helps us to picture there is an input impedance, and then there's the output impedance, and then we can think of a source there. So if this is 0, then this becomes the output voltage. Right? This is a source of power supply, if you like, in the op-amp. And this source is related to what we put in. So if this is 0, then all this becomes the output. Then infinite bandwidth means any frequency we put in, or the range of frequency where the gain is constant. And that A0 is we want it to infinite gain. The advantage is whatever we put in very, very small, it will magnify to very, very large. And then infinite slew rate. You want it something to be fast. Whatever we put in to come out very fast. Right? And then the other term that we encounter, saturation, occur when the output voltage reaches the supply voltage. Remember, the supply voltage allows us to amplify the signal, this input signal, to up to Vs, that's all. Because that is what we put in. Right? More than Vs, then it will cut off. That's called saturation. That means it cannot exceed that supply voltage, whether positive or negative. because that's what we provide for the op-amp. The output stays at Vs for further increase in input voltage. That's why we call cut-off or clipping effect, saturation. And we know that very small input differences will cause the op-amp to be saturated. Right? So another alternative way to say the flattening or clipping effect that stops the output from reaching its full amplified value. And then we go to roughly to there's your FM, we have your zero line, the earth line, and then we have two different power supply or two different set of battery. And this one provide a positive line. This battery provide a negative voltage. So we call it a dual or split power supply. Then we join them up. And we can put the input voltage. You can use a battery. Right? Same with the non-inverting. We can put a battery there also. We put a voltage and then we can put a voltmeter to read our output. Right? And we say that the power supply is usually from 5 to 15 volts. Very low power supply. Right? So very low current also. No. Very small difference in voltage can be amplified, but usually we don't use this small voltage. Right? Microvolt. And it will saturate. If our voltage difference is too large, it will saturate. And the polarity of the output depends on which input is greater. If the negative, the inverting input is greater than the positive, then it will go straight away because of the large amplification to negative supply voltage. If the positive terminal or the non-inverting terminal voltage is greater than the inverting voltage, then it will straight away go to positive Vs. Right? Comparator. Right? That's the purpose of the comparator. It compares the two input voltage and give us the output voltage, either Vs or minus Vs. So if your V plus is greater than V minus, then straight go to Vs. If your V minus is greater than your V plus, then it straight away go to minus Vs. So that's good as a comparator. It doesn't amplify, that's all. Doesn't amplify sound, right? But it's good as a comparator. That's all it's good for. Right? So weakness of the op-amp without negative feedback. Right? So far, the op-amp without any help from us, the gain depends on the internal component. As the components age with time, the gain is likely to change. As we cannot control, because all the components are inside. The higher gain would mean that it is not suitable for amplifying certain alternating voltage. That means it has limited bandwidth. Right? That means it's not good to amplify my speech, because my speech cover about 20 kilohertz from 0 to about 20 from 20 hertz to 20 kilohertz. So limited bandwidth means that whatever I speak, when it comes out of the loudspeaker, becomes distorted. Different from what my voice is changed. That's what we don't want. Want the operation amplifier to reproduce as faithfully as possible what I speak. How to use op-amp as amplifier? Right? Negative feedback. What is the feedback? Feedback is the process of taking some, either a fraction or all of it from the output and adding it to the input. So if it's positive feedback, then we take it from the output and we put it past the voltage with this resistor and back to the positive terminal. That's positive input, positive feedback, sorry. Right? Negative feedback, on the other hand, we take a fraction, a part of the output, and feed it back to the inverting input. So we take a fraction of the output and feed it back to the input. Usually we use a resistor to do that. Right? Remember, whatever we put in the inverting input comes out inverted. Amplify inverted. Right? And we give a beta, the feedback fraction, the amount that we feed back to the inverting input. Right? So that is what we put in. That's what come out. And that resistor that we use control the amount that we feed back. And remembering that this is a small amount, same frequency, all the same frequency, but this is smaller because of that feedback. We decide how much how much feedback fraction, right? You want smaller or bigger? So when this is added to this waveform by the principle of superposition, the net waveform is smaller. So that's why you find that as we feed it in, right, the gain becomes smaller. The gain, overall gain. Right? So overall gain, right, where we have a feedback or gain with feedback, or closed loop gain of the amplifier with feedback is given by this formula. You don't need to know how to derive it. Right? But we can learn something about that. It can be derived. Beta is the feedback fraction. Right? Fraction of the output of the amplifier that's feedback to the input, inverting input. A naught is the open loop gain, or the gain without any feedback. Right? That is decided by the engineer. We cannot change that. But we can change the overall gain, which is that A. Now look at the maths involved. Right? Basically, with feedback fraction, and there's an input, the two of them add together and finally go into the op amp to be amplified. Okay? And remember, this is inverted, so the waveform going in is smaller. Not this one anymore. Right? Smaller, so that's why it's coming out smaller. Okay, beta is negative. Remember, this is inverted, so beta is likely to be negative. So if this negative, negative becomes positive, and this value is going to be slightly greater than 1. If this is greater than 1, this is A naught, means that A is likely to be less than A naught. So the overall gain is smaller than A naught, smaller than the open loop gain or the gain of the amplifier. Or we say the gain of the amplifier is reduced. And we can also use negative feedback. Later on, we'll see in our example to reduce distortion in the analog system. The more feedback that is used, the more linear or accurate the amplification is, but also the smaller the amplification. No choice, right? We cannot have everything. So we have more negative feedback. As I say, the bandwidth better. And then the amplifier becomes more linear, more accurate. Advantage or benefit of negative feedback and increased bandwidth. Remember, bandwidth is the range of frequency where the gain is constant. Less distortion. We get exactly the same waveform as we put in, but amplified. Greater operating stability, because now our gain doesn't depend on what is inside the op amp. It's determined by what we use outside. And the gain is predictable because it depends on the resistor that we use outside. We will go into look at that in a while. And less dependent on properties of the IC. So the gain is controlled by the external resistor that we use. This is the input resistance. This is the feedback resistance. Let's look at the gain. Right? We can feed into the op amp a fixed amplitude, and we can change the frequency, and then we can measure the output voltage, and from output and input amplitude voltage we can calculate the gain, and we see without any feedback, right? There is the gain, there's the frequency. So it gives a variation of gain of the amplifier with input frequency of the voltage. When the gain of the amplifier is A0, right? Without any feedback, right? That's A0. The bandwidth is very small. About, right? This is not a linear scale. It's 10 to the power 4, 10 to the power 3 to 10 to the power 2. That means it's just 100 Hertz only, from 0 to 100 Hertz, which is not good. Not good for amplifying my speech, because my speech is from 20 to 20 kilohertz. Okay, so that's a limited bandwidth. High frequency are all amplified with different gain. You can see that. Different frequency, higher frequency, more than 100, they have different gain. So it means that my voice, my speech is going to be different from what you hear. Distortion. Okay, so if I increase the bandwidth to 100, 1000, I just draw a line there. Right? And in this case, my bandwidth is going to be 1000, which is improvement. So happen if we have a gain of 100. Okay, same thing. If we have a gain of 100, then we just draw a line there. That line there, we have much better. 0 to 10 to the power 4. That means it will quite close to all our audio frequency. Right? It's still not good. So we usually will have our gain smaller than that. By reducing the gain to instant 100, the bandwidth is 10 to the power 4 Hertz. This means for all the frequency equal or less than 10 to the power 4 Hertz, the amplifier increases the signal by the same amount. That's what we want, a linear amplifier. Okay, so that is our new formula that we need to remember. When the op amp is used as operation amplifier, the input signal must never become very large enough to cause the op amp to saturate. That's important point to remember. Otherwise, we have what we call distortion, saturation or clipping. We cut off the top there. It's completely different waveform from the input signal. There's a two new gain formula that we will need to remember. We'll go into that in a while. All right, let's start with inverting amplifier. We are required derivation of it. Okay, so that's your inverting amplifier. There is a negative feedback. It's applied by this RF. Right? Or this is a feedback resistor. An inverting amplifier produce an output that is out of phase, 100 degrees out of phase. Put positive in, negative come out. Right? Usually we don't show the power supply. Understood, you know that the power supply must be there because it's more, it looks more detailed rather than look a bit too confusing. And we assume that it's not saturated. The input going in between these two input terminal is not saturated. It's not large enough to cause the output to be saturated. And the gain is given by A equals to minus Rf divided by R1. Right? Negative because it's inverting, we put in here. Inverting terminal. So it's inverted, that's why I got a negative sign there. Rf divided by R1. You have to memorize and know how to use it. But we will derive it in a while. The gain is independent of the open loop gain. That means it doesn't depend. Yeah, there's nothing about A not there. So it doesn't depend on the gain of the operation amplifier. Right? Provided, of course, as we have gone over the theory, right? A must be less than A naught. And there's the input signal. And we apply it to this negative terminal. That's why it's called inverting amplifier. And then there's the output voltage relative to the ground. Right? So there's a negative here, applied by that resistor RF. So R1 and R2, RF and R1, right? These two resistors form a potential divider between the input, between the output and the input. Right. The other concept that we need to remember is virtual earth. In order for the amplifier is not saturated, we don't want it to be saturated. So in order for it not to be saturated, the two input, B negative and B positive, must be almost the same, very close. The non-inverting is connected to zero voltage. It doesn't have to be connected to zero, but usually for your stage, we connect it to zero voltage, right? Or the earth line. Thus, the inverting input, this positive one connect to earth. So that inverting input, that point there, must be also close to earth, zero. Right? Or we call it virtually zero or virtual earth. That point there. Right? That point there is your virtual earth. Right? It's not connected to earth, but because of this zero, we want this one to be zero. It's called virtual earth. How do we make it to be virtual earth? Right? There's a feedback resistance. How one becomes your input resistance? Virtual earth is due to the op-amp having infinite gain. Very, very large gain. And the non-inverting input is at earth potential. That means this is at earth. Positive input terminal, earth. So the negative input terminal also at earth or zero voltage. Right? Because that's what we want. Amplifier not to be saturated. Both of them must be zero. Right? So the inverting input, right? That input and that input must be near to zero or same potential. At that point there is your virtual earth. In virtual earth approximation, right? Near to virtual earth approximation, when the inverting input can be taken as zero. Right? Remember, this is earth, the positive input, negative input here is taken to be zero. How to make it zero? How to make sure it's zero or almost zero to find significant figure? The input resistance of the amplifier is equals to R1. Right? That means if that is zero, this is zero, there is no current flowing through that input impedance of the amplifier. That becomes the input resistance now. Okay, so when you are asked about virtual, you can see that usually there's a lot of points given. So you have to memorize all that. This one also depends on the number of points given. Right? You want it to find significant figure. Why to find significant figure? Right? Remember this calculation that we did earlier, this example. Right? This one, to find significant figure, there's a there's a difference, the difference of about 0.0030. Right? You can see when it amplified, it can amplify, but we don't want it to be amplified. We want it to be smaller than that. That's why we have to have 5 significant figure of 5 decimal places. Okay. Okay. So virtual Earth basically means 0 volt. We didn't connect to Earth, but it looks as if it's a virtual Earth. It's 0 volt. The input impedance itself is very large. So if this is 0, this is 0, the input impedance here is very large. So no current will flow into the op amp. Right? Remember, these are all theoretical. So that point P is your virtual Earth. Okay, let's now derive the equation. This means that the current I in, the current, as it comes in here, it can be going in from here if this part is positive, or if this part is positive, this part must be negative. Remember, it's inverting. Then the current can be flowing from here, right? But let's say this is positive, the current is going in to R1. Then it doesn't go into here because this is 0, this is 0. It goes out there. RF goes here, then it comes out. And remembering that because of we feed into the inverting input, there's 0 current flowing into the op amp, the output is inverted, or we say anti-phase, or 180 degrees out of phase. Anti-phase, 100 degrees out of phase, or inverted lah. That's all the different terms we use. Means the same thing. Right? Whatever we put in comes out bigger. Same frequency. That's how it's amplified. Okay, let's derive it. Kirchhoff's current law. We use Kirchhoff's current law that you study in your AS physics. Current in R1. There's a current in R1 equals to current in RF. Nothing flow into the op amp. Okay. That's a 0 point. The point there, P, 0. So it's always starting from positive terminal minus a 0 divided by R1. Is that current I in? And then remember this is negative. This is positive. So it's 0 minus that divided by RF is RF. Okay. And we go to our definition of gain. Definition of gain is whatever is output voltage here divided by the input voltage there. Okay, so from this equation, we take our V in down, cross multiply, take RF up, and then take this negative side to the other side. So that's what we get. Okay, take V in down, that's how we get our definition for gain. Take our RF up, and the negative side across that we get minus RF R1. Now you are required to know how to derive. Okay. Now we go to non-inverting amplifier. Yeah, you're not required to know how to derive. Right? So we are not deriving it. Right? There are only certain amount of derivation. We don't want to make too many because you don't enjoy anymore already. You get lost already with all the derivation. Derivation can get it from textbook. Okay. Same thing. A fraction, that's the output. We take a fraction of it, and the fraction is determined by RF and R1 here. Right? With feedback, remember, we call it non-inverting. That means the feedback, the input, the signal must go to the positive terminal or non-inverting terminal. That's why it's called non-inverting amplifier. Right? But it still got negative feedback. You still feedback the output to the inverting terminal. The input voltage V in is supplied through a to the non-inverting input. That's what we mean. Apply to the positive terminal. The output voltage V out is in phase, right? Because whatever you put in comes out amplified as well, not inverted. That's why it means in phase. Okay? Remember, this is a non-inverting, not inverting. And as we say, negative feedback is provided by means of our potential divider, RF, R1. And you're required to know, to remember this formula, you add the two resistance divided by R1. Okay, let's complete that. Now let's go to our worksheet. Okay, have a look. Observe the circuit and answer the following question. Is there a negative feedback? Now you should be able to decide. Yes, there is a negative feedback. Right? It doesn't have to go through here to come back here. Right? Whether positive or negative is up to us to put, but it's feedback from output to the negative terminal here. What type of amplifier is this? Then we look at amplifier, then we look at where is the input. Input is here, and it's to the positive. So it's a non-inverting. What's the gain? Memorize formula only. Right? Negative R minus R2 divided by R1. Sorry, this is not a inverting. This is a non-inverting. So non-inverting, you add the two resistance and you divide by R1. This one. That is two resistance divided by R1. Okay, let's look at another circuit. Observe the circuit and answer the following question. Is there any feedback? Yeah, it's a feedback there. That's the output. You take it to the negative terminal. So there's still negative feedback. This side is the input. That side is the output. What type of amplifier is it? Is it inverting or non-inverting? Now you can see the signal is going in from here. The positive input is connected to earth. So this is a inverting amplifier. And what's the gain? If it's inverting, right, it's minus R2 divided by R1. Minus must be there because it's inverting. Okay, observe the circuit and answer the following question. Is there any feedback? Yeah, there's a negative feedback. 100%. What's the gain of amplifier? 1. What do you call this amplifier? Voltage follower. What's the advantage of this amplifier? Right? Remember? Of amp. High input impedance, low output impedance. That's the advantage. So if you have a load that is of low resistance here and got a source of high resistance, you connect the source to the load directly, and you have a problem. The signal coming to the load will be very small. So this type of amp can be a middle stage, or we call it impedance matching. Right? That high impedance and that high impedance, it means that this one is higher than that. So all the voltage from that source will go to the input here. And then you don't have to amplify anymore. Whatever comes out will go to the low output, to the low resistance load. Is it an inverting or non-inverting amplifier? This one I must be able to decide. Right? This is a positive terminal that we feed in the signal. So it's non-inverting. And state the likely value of R1, RF, and R1. RF is here. Right? RF is here. So RF is likely to be 0. a short circuit, if you like. And R1 is likely to be infinite. Then we look into that in a while. And V out is straight away going to be V in, exactly the same, because the gain is 1. Right? Where your RF is 0, both of them, so it's R1, cancel R1, you get 1. Gain is 1. Right? There's one thing though, it doesn't amplify, doesn't change the bandwidth is still very, very high. So the output and input are in phase. Okay, what we have done? Let's look at the same circuit again. Right? We are just using this circuit, except what have we done? We put this as 0. And R1, what have we done? Right? We cut it off. So it means that we put R1 as infinite. Yeah, infinite resistance. We cut it off. Then we use that formula. That's how we get our gain equals to 1. Right? RF is 0. R1 and R cancel becomes 1. Right? So you have a advantage of this one is got high input impedance, low output impedance. Okay, so a voltage follower is used as a buffer that is to connect a high resistance source to a low resistance load or impedance matching. The output of the amplifier is joined to the input, to the inverting input. Right? Here's the output, straight away to the inverting input under feedback. So if that is high, that is low, that is high, it's not good if we connect directly there, because the output voltage here will be very, very low. So if we use this one between these two, then we can have a high voltage also here. Okay, let's look some question. This is a past year question. It's an old one during the I think 96 June paper. State the type of amplifier. Right? You should be able to decide 3 of them only. Either it's a comparator, non-inverting, or inverting amplifier. So there is no taking anything from output to the negative terminal. Right? This is not. This is just your biasing. Right? Biasing. So it's a comparator. Identify A. That one, diode. This one, if you like think of it as light, so LED. What is the function of R? Right? A student decided to build a device to monitor at a distance whether the door is open or closed. Right? Sometimes we may not be able to see whether the door is closed or open, but we can have a device attached to a door to tell us whether it's closed or open. He fitted a switch in the door frame so that when the door is closed, the switch is closed. The door is closed, the switch is closed. The switch S is included in the circuit shown in figure 9.1. That's a figure 9.1. What's the function of R? Function of R, remember, there's an impedance here, input impedance. So you want to have a closed circuit there. When this is open, you have to have a closed circuit there. Then you can decide these two, which one will light up. Right? Provide a return path for the current. Deduce the state of the light emitting diode A and B when S is closed. So when S is closed, what is going to happen? You force this negative input to plus 9 volt. The positive is at 1.5. Right? This is 9 volt, this is 1.5. So 9 volt is greater than 1.5. So it means that the output will straight away go to negative because the negative terminal is greater than the positive terminal. So it go back to minus 9 volt. Saturated, straight away 9 volt, minus 9 volt. So minus 9 volt This minus 9 volts, so this becomes a reverse bias. This is forward bias. So this is the one that light up. This doesn't light up. Right? So B is off, A is on. What change, if any, occur in the state of A and B when S is open? When S is open, what are we doing? We are connecting this negative to this minus 9 volt there. Right? So it means that, remember, there's a very high resistance inside there. So it becomes a potential divider. So it means that that voltage is very close to minus 9 volt. So it's going to be less than 1.5. Okay, so it means that the positive terminal is now greater than the negative terminal input. So it straight away go to 9 volt. This is 9 volt here. 9 volt, 9 volt. This is reverse bias. This is 9 volt. This minus 9 volt. This is forward bias. So this is the one that's conducting. Okay. This is off. This is forward bias. Right? This one is called protective resistor. To protect this one, because we will study this later on in our last topic. Because this one take low resistance. Sorry, not low resistance. This one take low current. This one, the LED. It occurs too high maintain machine. So we can protect it because you want to make sure that current is not too large to damage the LED. Okay, let's try another example. An AC sinusoidal voltage of root mean square 2 root 2 100 Hz. This 100 Hz is 2 root 2 is applied to the non-inverting positive terminal of the op-amp. State whether it is non-inverting or inverting. So we feed it into the positive terminal here. So it means that coming out will be the same. So it's non-inverting amplifier. What is the gain? Right? If it's non-inverting, we add these two resistors divided by this one. The formula. Memorize the formula, calculate out. So it's 4. The gain is 4. Calculate the peak voltage and the period. Okay, we got our root mean square value. So the peak is given by root mean square times your root 2. Put in our value, 2 root 2. Root 2 times root 2 becomes 2. So it becomes forward. Okay, so before we can sketch part T, sketch the input and output waveform, we must first convert its frequency to period. Okay? So divide by 100. We want to change it to millisecond, we times 1,000. So we get 10 milliseconds. Okay, so choose our proper scale. Usually it's come out again, they will give you a scale. They will draw for you. And then you just have to sketch that. They don't want you to waste your time drawing the graph. Okay, so that's the period, 10 milliseconds. Draw that. Right? And we get the output voltage. The peak value is 4. Right? It's a non-inverting amplifier. Gain is 4. Output is also 4. Peak value is 4. So now, remember, it's non-inverting. So if the gain is 4, that highest point 4, we times 4 is 16. So that's how we should draw 16. Right? Usually we should draw lightly lah, or dotted line. Then remember, our supply voltage is just 10 volt only. So it means that it will cut off, or clipping effect, or saturation. Right? At 10 volt there, you will just cut off. So you won't see the original waveform. That's what I mean by clipping effect. Okay? 10 volt there, somewhere in the middle there. clipping effect. Right? Too high again. Sketch the output versus input characteristic. Right? Here we want output, input. Remember our gain is, our supply voltage is 10. So it becomes saturated at 10. So you want to know when it becomes saturated, the voltage input when it becomes saturated. So we go to the right, V in is V out divided by gain. Okay, put in our value 10 volt, gain is 4, is 2.5. So we can draw about 3 is about here, so 2.5 is about there. Okay, and draw a horizontal line there. Same, the other part for the negative side, same thing. And after that, you can draw a straight line. Suggest how you could record the distortion. How can you reduce the distortion? Or how can you remove the distortion? Right? It cut off. Right? Remember that. Right? 16. So if we want to have 16 there, then we must increase the power supply to 16 or 17. Then we can see the waveform. Or alternatively, reduce this gain. Right? So instead of 4, we can use gain 2 or 2.5. 2.5 will be just nice there. 2.5 times 4, right? Then 4 times 2.5 is 10. Just nice. Okay? So we can reduce the gain. Two things that we can do. Increase the power supply to plus minus 16 volt, or reduce the gain to 2.5 or smaller by increasing R1. Okay, so we have completed for this part. As I say, the notes can be obtained from my Facebook. Right? That's my Facebook under A-level Physics A2. Notes, PowerPoint, and video can be obtained from there. Or, and if you want to do some practice, try the partial question, you can go to Physics partial question A2, right, where you can find a question from 2001 to 2010, topic by topic, to practice, try out. Right? The marking scheme is also there. Okay, or if you don't have an account on Facebook, you can go to YouTube under my name, and then you can find it under 21.1 amplifier circuit. Okay, so thank you for today. You are welcome to ask questions on my Facebook and the YouTube there. I'll answer you there.